Cool. I guess we can first recap what we done last week. Um, no questions on homework or submitted. Nice. Cool. So last week we were talking about music classification. So that's the simplest form of machine learning task that you can do. So basically you just be creative what you want to predict and try to get those data. Then you can sort of like follow whatever people have been done in machine learning or deep learning, then just applied it to some music classification tasks. So that include a bunch of different tasks like genre classification, mood classification, instrument recognition, as you did in homework 3, and composer identification, key detection, core estimation, or music tagging, which just cover everything above. Just treat everything as a tag. So it could be applied for a bunch of different cases. For recommendation system, you want to see what to play next. So basically, you should have a sense what your pool of music is like, or your corpus, or understand what your data or what your products are from the perspective of the streaming service company. And we do also have, playlist generation. So think about once you know what these songs are about, then you can sort of like create different playlists based on the genre of it, or different composer, or typically those information will be available. But sometimes if you're thinking about building an app on a user uploaded forum that potentially you don't have all the information, then you potentially want to use machine learning algorithm to guess what those metadata are. So in terms of like specific types of classification tasks, generally we would just classify, I don't know, categorize these tasks into 3 categories. So, binary classification, multi-class classification, multi-label classification. But basically that means what's your output space is like. If your output space is just like 0 and 1, true or false, it's classical or not in this case, then pretty much this is like the standard way. Just go through some neural network, and then at the end, you applied a sigmoid function to sort of like create that artificial thresholding thing. So, with different songs, you get different numbers in the end after the sigmoid. Then you can set a threshold to sort of like determine what your output is like. So, be anything above that threshold, say in this case 0.5, then you say yes. Anything below that, you say no. So in homework 3, we were doing multi-class classification. So, we have a bunch of different output, so 11 classes. And what we want to do is to sort of like come up with a probability-ish, estimate at the end after your neural network. So that's why we apply a softmax at the end. So you see, that sort of like sums up to 1. So you get the highest activation in flutes. So, you just say, well, we think this is a flute. That's the prediction. So multi-label classification is a bit more complex, where you have multiple labels. So what we want to do is to do tagging. And they basically, the most common way we talk about, I think last week we just ends at, power set expansion, where you just go over all the different combinations of labels and then do multi-class classification. So that's the least popular way of doing that. But the more popular way to do it is through binary classification. So basically you have some audio, and then you go through different neural network. They could potentially be the same network, just that in the end, the last layer, you go to different classifiers in the end. So these could share weights, or they could even be the same neural network, just that, in the end, you just do a different classification, do a final projection layer to different genre. So you just do binary classification through, it's classical, it's soul, it's pop, it's rock, it's R&B, blah, blah, blah. Cool. Then now let's move back. to where we stop. Where are we? Cool. So last week we sort of like stopped somewhere here. We have this like power set, label power set that basically cover all the different combinations that it's less efficient because it would be 2 to the n minus 1 combinations. Think about it, it's crazy large. Then input in terms of like input features for your classification model, either we do waveform or some time frequency representation, spectrogram. So these are the raw data format that we typically use for music, but it also applies to general audio. But at the same time, you could also use handcrafted features or features provided in metadata to do better classification. So that includes a bunch of stuff. Acoustically, you can just measure the loudness, compute RMS energy, or try to guess what the decibel is, and detect the pitch, or try to figure out what the timbre is like. And rhythmic, you can also try to predict the beat, tempo, and time signature. Sometimes those are available in metadata, so you can do better classification in that case. Tonally, you have key scale chords, and also instrumentation, expressions, and structures. These are things that people have trying to figure out how you can predict those by handcrafted features, but also sometimes those are available in metadata. So here's a bunch of like common data sets. So, unless you want to train some models, pretty much you would just grab some existing model and do it. But these are some of the common data sets. So, you can definitely see how the history evolved. So at first, this is what people are using, GTZen, which is like 1,000 songs in 10 different genres. So, 100 songs per genre, 30-second each. So that has been the standard for, I think, like 5 to 6 years. And then people started to do something else. And so, likely the most famous one is the million song data set, which is very tricky to access the audio files, but somehow people have shared it, in the academia. So somehow you can still get it, but just tricky to access. There's also free music archive where you can just Google this, you will find a website where there's a bunch of free music there, like public domain or CC license-ish. And Jamendo is another website where they have like CC license audio and music. And audio set is a large data set, which is just YouTube URLs, but it generally contain low quality, especially for music. And since it's what we've been doing, but this is not technically, a music data set, but more like, a bunch of instrument sounds. Cool. So finally, I just want to talk a little bit about evaluation metrics. Most of the time, you just grab existing models or try to see how it works, unless you want to actually dig into how classification work. Otherwise, pretty much a few of us will look at the evaluation metrics. Usually we just look at the accuracy. If it's good enough, then we just use it. But so to give you a sense how we do evaluation in these research. So I guess the key of evaluation metrics is that it has to capture what you care the most. So that would be the ultimate goal of what an evaluation metric is. So the best evaluation metric depends on the actual use case. So think about classification, genre classification. What do you want to do with genre classification? Do you want to send it to the user, or you want to do curation, or you want to do playlist generation? What's the goal of your your use case? And that will you will better understand what the best evaluation metrics to be used. So in general, it's always good to use several evaluation metrics to obtain a more high level view of your model's performance. So some of the easiest, evaluation metrics, likely, in homework 3, you see the accuracy. So accuracy is the most simple one. So imagine this is like a toy example where we have a bunch of data. So stuff in the blue. So the colors here is the ground truth. So, we have a bunch of data. We don't know what those colors is, whether it's positive or negative. But anyway, we do know that ground truth is that there's a cut here. So everything at the left should be blue. Anything at the right should be, orange. So positive and negative. So imagine that you get something like this, mostly good, but that, you did something wrong here, and you also did something wrong that, incorrectly predict something should be negative, but you predicted it as, positive. So basically there are 4 keywords that you should know, true positives. That means that you predicted positive and it's true. True negatives, you predict it as negatives and you are right. So the more confusing one is false negative and false positive. So false negatives basically means that, well, you predict it as negative, but it's wrong. So its ground truth is actually positive. And that's the same for false positives. So the actual, false positive or true positive, the last word means that what your prediction is. So in terms of like accuracy, that's the simplest way of doing evaluation. So that's what we've been doing in homework 3. So basically we just calculate the percentage of correct predictions across all classes. So basically you just look at your classification. So if the blue one is lie in the blue area, then basically it's a correct predictions. So in this case, we only did wrong for 4. So how you compute that would be something like this, look at all the samples that you have, you do correct on the positive case, you did it wrong, you did it wrong for the negative case, but you did it correctly on the negative case. But anyway, you just look at how many correct ones you did. So this would be the, accuracy. So something more fun, I guess, is to look at this confusion metrics, especially in the multi class classification case, as we will see later. But, in the simplest form of binary classification, you see these, true positives where, at the x-axis, you have the prediction, so positive, negative, and at the y-axis, you have the ground truth, whether those are positive. So the tricky part would be, if the ground truth is positive, but you somehow predict it as negative, then it's a false negatives and, false positives. So, a concrete example would be, is like a cat prediction that, false negatives would be, a cat, but you sort of like predict it as not a cat. And false positives would be, it's a dog, but you predict it as a cat. So, the key is that the positive and negatives here correspond to the predictions rather than the ground truth. Cool. So accuracy is good most of the time. But one thing that accuracy doesn't work well is on imbalanced data set. So, most of the time when you work on machine learning, you start with something that's, pretty balanced, your data sets. So, think about most of the machine learning data sets, they sort of like have, say, 10 classes, and they try to make it, sort of like assuming those classes are, equally distributed. But think about one thing about genre classification is that that's usually not the case. Think about pop music and think about, other genres. Likely you have, I don't know, 10 times more pop musics, usually in, randomly selected collections of data that's available to you. But you also think about instrument recognition, piano, guitar versus, I don't know, tuba or, double bass. Piano and guitar would be much more popular to commonly seen in your data set, most likely. So those are cases where we do have that imbalanced data sets where, the distribution of your labels are is not uniform enough. So, take a disease with a 1%, prevalence, for example. We could just say everything is negative to all diagnosis. And in this case, you will sort of get 99% accuracy because you only did it wrong for one single case where you say negative to the actual positive case. And that's the only one you care, and you just miss it. But you sort of get 99% accuracy. So that basically means that accuracy is not so sensitive to that in terms of how what's the percentage of the things that you care. So in this case, it's an imbalanced data set because 99% of time you are predicting a negative, but only 1% of time you predict a positive, and you care about that. You don't necessarily care about, just giving all the negative things, especially for, cancer detection. You want to see if you can grab that, and you are fine if you do some false alarms because it will be much easier to handle with. So basically, there are two more evaluation metrics that you should look at. So one is precision. I would just go over the definition, and at some point, you might realize that accuracy doesn't work in your case. Then you might need to look at precision and recall. But at this point, you might be wondering why we should care. But at some point, you will realize that if your data set is in that shape, then you have to use this. So precision is defined as, true positives over true positive plus false positives. So basically, look at the definition is that, for everything you predicted as true, how many of that are actually true, or how many of those are actually positive. So, in this case, you do, sort of like 12 predictions for stuff that's positive, but only 9 of those are actual positive. So only 70% rate or probability that whenever you predict something as positive, you get it correctly. And that's positive. So how often predictions for the positive are correct? So this is the definition of precision. And we also have the definition of recall, which is, true positive or true positive plus false negative. But look at it. It's basically, for everything that's positive as your ground truth, how many did you actually collect? So, in this case, it would be 0.9, so 98%. So how well the model finds all positive instances in the data sets. So this will be, more important in the, the example that we just saw, rare disease detection, where you just want to find all the positive instances. You care more on this than, actually, some of the false alarms. So, these are the two most common examples of precisions, how often predictions for the positive are correct. So you look at, these are false alarms. So in case you care about false alarms, then you have to use precision, care more about precision. So recall is look at missed detection. So whenever you have a bunch of missed detection, then your recall will be lower. So if you care about missed detection, then you should do care more about recall. Cool. So, intuitively, precision measures how often predictions for the positive are correct. And recall measures how well the model finds all positive instances in the data set. So when should we care about precision and recall? We just talk about this. Should we aim for high precision or high recall for rare cancer detection? Yeah. Yeah, we just talked about it. So, recall, look at this case, now we have shifted, positive and negative case, because, in rare cancer detection, we basically have fewer positive case. So, the shape actually changed. So we have fewer. It's actually much, extreme that, potentially you only have one ground truths as positive. But anyway, this is just an illustration. So you have like two things that you have to care about, either false negatives, which are, things that should be positive that you didn't capture. So these are missed detection. False positives would be, false alarms, where those are not a cancer, but you just predict it as a cancer. So in this case, think about rare cancer detection. Most of the time you care more about misdetection rather than false alarms. False alarms, you just figure out some way and later try to do more, CT scan or, MRI to see whether it is actual tumor or, cancer diagnosis. But, if it's a misdetection, it could be worse consequence. So in this case, we care more about, misdetection rather than false alarms. So we should aim for, high recall, ensures that most cancer cases are identified. But, think about music recommendation. Should we aim for high precision or high recall? I guess it's very obvious. It shouldn't be high recall again. So, in this case, we will talk about recommendation system later, but, most of the time, if you want to build a recommendation system, what you start from is to figure out how can you do better on getting a high precision model. So again, look at the same data set. Well, there's a weird animation, but anyway, you have, false alarms and missed recommendations. In this case, false alarms is much more unwanted because, if users think about music search or recommendation, if the user asks for rock music and somehow you just get a classical music into that recommendation, they will be like, what? It's going on. So, that's something that you don't like. But if you have like missed recommendations, say, the user is actually thinking about a specific, artist, but you didn't, recommend that, but it's actually better than, false alarms. So, in this case, we usually tend to start with high precision model and later figure out ways to improve that. But, at least high precision ensures that the model won't recommend irrelevant items. So in this case, recommendation system, most of the time you will see people are comparing precision, but sometimes, F1 score, which we'll talk about. But, precision is more important in this specific case in music recommendation. So anyway, we have precision and recall. And, once you define two things, and then, people will, again, want a score that could just combine those together. So, F1 score is a way to combine those, and it's particularly useful for imbalanced data sets. It works better than accuracy when the data set is imbalanced. So say, music search, retrieval, and recommendation. But anyway, this is the definition. So it's a harmonic mean of it. It's very unintuitive what it means, but the idea is just to figure out a way to combine both precision and recall. That's all you need to know. And if you really want to dig into how these metrics work in different scenario, they tend to use different score in general. Cool. So that's pretty much what we should cover in evaluation metrics. There's a bunch more, but these are the simplest forms of evaluation metrics. So going back to confusion metric, which is more interesting, for binary classification case, this is what we get. But more interestingly, look at multi-class classification, not multi-label. Let me fix it right away. So this is the case in our our homework 3, where we have a bunch of predictions. So this is actually the model that I trained. So in the homework 3, the example 1. So you can actually see, we can plot this matrix, which is called confusion matrix. So basically you do, the ground truths at the y-axis and you do prediction at the x-axis. So confusion metric is a way to look at how you do well, how you did getting different, ground truths stuff to, ground truth class to different prediction. So, it's always nice to look at confusion metrics because it will give you a sense whether your model actually learning something meaningful. So if you look at this, there's this purple stuff here. So, when we look at this, we look at the rows. So, for all the ground truth that space, part of it, most of the time, is predicted as space. So, that's nice for our model. Usually you see a strong, bright diagonal because, you want, if it's a base, you predict it as space. If it's a brass, then you can predict it as brass. If it's a flute, then you predict it as a flute. So that's usually the case. But whenever you look at those other, round predictions, so, this basically means that bass sounds got classified as keyboard sounds. So that could be possible. That's not totally off. But you can also look at this, guitar sounds got classified as bass, which is pretty reasonable because, bass is just bass guitar. So it depends on the frequency range. But, if somehow the guitar sounds just sound very low frequency, then inherently there's no way you can guess whether it's a bass or a guitar. And it also sometimes got classified as keyboard sounds. So, keyboard sounds can also be confusing. What keyboard sounds are you talking about? If it's a piano, then it's obvious. But if you think about keyboard, it could be any sound. And here, organ sounds get classified as vocals, which is not ideal, but in terms of VST. So this is like sample instruments. So vocal usually have that, they actually have the same sounding features that is airy and sounds more like vocals in this case. So look at the confusion metrics, you can get a sense that how your model do well. If somehow your organ being classified as, I don't know, organ classified as strings, then that's less, obvious or less reasonable, then your model might be doing something wrong. So, confusion metrics is also a way to sort of like evaluate your model, but in a more, I don't know, indirect way that you have to look into what that actually means. Cool. So most of the time you won't be looking at evaluation metrics, but unless you want to train something. Cool. So there's a nice tutorial. Lots of the slides are actually based on that, which is a Izmir 2021 tutorial, where it has a really nice, these are the folks. So it has a really nice wiki, not wiki, Jupyter book. So it would talk about everything, input representation, data set, proper formulation. And, we didn't cover all of these, but there are a bunch of different models. We mostly talk about supervised learning. So, look at different classification model. They talk about, there are a lot more. So, in our case, we just do convolutional network, but there are a bunch of other case that you can use other architecture to do it. You can also just do it on waveform directly. And augmentation and semi-supervised learning, which is a way to sort of like go beyond supervised learning where you don't have enough data. Say you have a bunch of data, but you only have 10% of those are partially annotated. So how can you do better on that? And they're also self-supervised learning, which means that you don't even actually get any labels. Can you do something from that? So a bunch of resource here. So if you're interested in, you can look into it, but that go really deep into what the architecture is like. Cool. And there's also like open source music classification models in case you want to use it, but there are also some online service. These are open source models, but there are also commercial models. Cool. Or you can just upload to YouTube, and YouTube sometimes will suggest text for you. That's another way. Cool. Any questions? Good. Cool. Let's move on to today's topic. Cool. So today we will talk about source separation, which is important. But AI or not, I guess debatable, but this is one of the features that being used again and again, either in creative workflow that you want to potentially just extract some stem out so that you can do sampling or remixing, but also think about a lot of like MIR tests that you want to say predict like who the singer is, then you should get the vocal track only rather than the whole tracks. So source separation is something that's being used intensively in different use cases. So that's what we would be talking about today. So source separation, in a nutshell, what we want to do is that, you have some audio, sounds like this. I think I just go to a website where I can find not bad, but we have a bunch of like instruments, and what we want to do in source separation is just to get all the stems out. So these are the output that I got from one of the platform that we talk about, Moises. We can get actually free access for students, so we will look at that later. But these will be just. Do you remember the days when you said nothing gets in your way? Yeah, so it has the reverb here. Actually, it's much easier for the model to get the reverb than not the reverb, because source separation, we usually get the wet audio outputs usually. So what we did is that these things should add up to this. So actually, it's actually much harder to get dry sounds. So usually we will get the reverby, reverb-ish.
Usually like it's always cutting in and out of the reverb, and it's like really messy. That's like super clean.
Yeah, so that's state of the art somehow. These are commercial products, so it's much better than the stuff that we see in academia, because usually they have much better data set to train it. So this is the piano track. I don't know if these are classified keyboard rather than piano. The drum is also really good. It's true. No, I think I put it at wrong. Maybe this is wrong. Hopefully this is wrong. Let's see. Well, that's not drum. Where is the drums? Maybe this? This is bass. Okay, bass is good. So likely this is drum. Yeah, so this is likely drums. I probably messed up with the order, hopefully. Oh yeah. So I did mess up. Cool. So that's pretty much what we want to do. We have mixtures, and what we want to get all the sources, like vocal, keyboard, bass, guitar, and drum. And sometimes we also have that track as other. So basically everything else. Because sometimes you don't have these sources, and sometimes it's hard to define whether they are in these predefined categories, and you just put it in something else. In this case, I mess up with these two, but this will be the drum, and this will be the something else track. So somehow the model think this is something else, but it depends a lot on the music. But there's fundamental challenge in this case. Vocal is much obvious to extract from others, and also drums and bass are much easier than others. Sometimes keyboards and especially like strings and sometimes guitars, those are much harder to define because it's fundamentally ambiguous in some case, especially when you're doing electronic music. But so separation also go beyond that. You can think about even trickier one that you have drum, like a drum. Wait a second. That's the bad audio interface of my laptop, which is unfortunate. But anyway, this is what it sounds like. Well, so for our model, not our model, but I mean for commercial model, you can actually even extract out the specific drum from the model. So this is the bass drum. You also have the snare drum. You can get the hi-hat, open hi-hat, closed hi-hat. And you can also get the toms like this. And cymbals. Oops, tricky. So, it depends on how you frame it and what do you have as the data to train these models. But this is sort of like what current commercial, model can do. Cool. And so basically, source separation is what you see here, that you want to just separate out all the tracks. And it's called different names. In Logic Pro, we have the stem splitter. Basically look like this. You can sort of like choose what you want to split. Usually, as I said, that vocals, drums, and bass is the easiest one to differentiate from anything else. And usually we put all the other instrument into other. And that's the case you saw in our example where guitar, keyboard, synthesizer, and strings, they can be kind of confusing to do, define which one is which. But drums and bass is much easier to define. So this is like Logic Pro. You can use it in some more recent version, I guess. But that's called stem splitter in Logic Pro. And you can also do FL Studio, where I believe you can right click on a sample and you will see extract stems from sample. And pretty much you can do the same, drums, bass, vocals, and other, so instruments. And you can just do it. And it will process here. There's the progress bar. And I tried to Google whether other DAWs have that, but it seems like nope, only FL Studio and Logic Pro currently have this function, but we will likely see most stuff coming up. But at the same time, you can also do plugin to get these features, as we will see later. So separation, also known as stem separation or stem splitter, just different name, and it's stem extraction. That's more common in commercial software, but in academia, we usually call it separation. That's the technical terms to define it. And sometimes it's called music demixing. It's slightly different meaning. So music demixing is sort of like the thing we talk about, you hear that reverb in the vocal. So, if you want me to define demixing, I would say you probably also want to remove those effects. Music demixing could be something slightly different, but, sometimes it's also the same, definition of source separation. And sometimes you have stem extraction. So slightly different meaning. So stem extraction, meaning that you just want to extract one single track out and everything else, rather than you just want to split them into a bunch of different tracks. Cool. So these are just terminology, but pretty much they are all based on the same technology in some sense. So one thing to be clear is that source separation does not remove effects. As we heard that in the vocal track, you hear a lot of reverbs. So in this case, this is just a short, brief, I don't know, high level illustration of how music production can work. So, it's much more complex than that, but, imagine the simplest form that, well, you do have a bunch of different instruments, you record them with clean signal, dry signals, and somehow you go through some of the effects, or, you do mixing, or, you have, compressors, EQ, blah, 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 all the different effects. And then you get some, wet audios out. So that's what we call wet signal audio signals. And then finally, you add them up to get your mixers. So usually we call these, clean sounds that going out from your instruments. Say, you record the drums or you record the vocal. It's very dry and, close recording for most case. And then after all the effects, you apply reverb, apply different stuff. Then you get the wet signals. And the final mix would be sort of like summing up all these signals. Sometimes it's much more than just summing up, but you can pretty much assume it's sort of like summing up in some sense. So, source separation goes from mixtures to the wet signals. So that's the key. We don't do it all the way back to the dry signals. So we usually only output the wet signals, because the way how we define it is that, we will predict something that sum up to the original mixture. So going from wet signals back to dry signals is another task, which is called effect removal. Maybe, hopefully, we will cover it in the last few lectures of the course. We will talk about how you can do effects, and effect removal is also part of it, but how you sort of like modeling effects using AI, which is very popular topic nowadays. Questions on this? Cool. Oh yeah.
Dry signal. I know there has been like deep reverb, deep click, deep breath.
Yeah.
Ozone, RX7 can do like deep reverb, but like other effects like decompress. I mean,
yeah, definitely.
you
Yeah.
don't really need to do that with machine learning much.
Yeah, pretty much you have to do machine learning, because in some cases, think about decompress is sort of like generative in some sense, in that, you actually lose part of the dynamic range and you want to recover that. So you are actually doing generative task in some sense. And that's why people are using deep learning. There's a very cool work. Let me see if I can find it right now. Decompression using deep learning, which is a WASPA paper from, well, I couldn't find it right now, but I mean, there's a paper that just like expand the compression, dynamic range and try to recover that, which is unfortunate because we now have the loudness war that people just, use a bunch of compressors. But in terms of effect removal, general audio effect removal, this is the models that, sort of like cover all general purpose audio effect removal. So you can sort of like say reverb sounds, and they can do this. This is their model. So this case is that you don't know whether it's a reverb or not, but try to guess whether it's a reverb. But if you know it's a reverb, you can and compress it. And delay. Distortion. And then
Not as hard. You just such a like high cut, right?
distortion, but distortion is like, how do you recover that? Right?
Well, at least like desaturation.
Yeah, so desaturation sort of like meaning that you have to create something new. So it's actually much harder than, reverb, because reverb is like you are adding different, version of the original sound. So you are removing stuff. But distortion and compression, if you want to remove that, you actually need to add new stuff back to that.
For saturation, it's just adding upper harmonic. So technically, I feel
But
like
that's the key.
the one
Yeah.
time you don't need machine learning because.
No, I mean, I would say you actually need machine learning to get all the harmonics because, harmonics that's the timbre is about. Most of the timbre differ in the higher harmonics. So that's where you see why some violin is more expensive than the other is in the higher, harmonics. Usually the low harmonics look the same across all different instruments. So the higher harmonics is the key to timbre. And in case of distortion is that you actually break those. So they are gone. So you have to predict the back. So in some sense, this is sort of like you don't know what the ground truth is. Listen to the distorted input. So sometimes it could be kind of confusing. They can also do multiple effects, but it's much trickier to get it right. Let's listen to this. And the output. Well, to some extent. Like a bass drums, I guess. Well, not bad. Yeah.
With this, like, would it when it's inputted into this, like, would it know that it's that like the effect on it is reverb or the effect
so that's the difference here. So overcode means that you know what those are.
Okay.
So detect is that they actually have a model to detect what the effects are being used. So they basically just have a chain of effects and they try to remove that. So this sort of we will cover this later, but sort of in some sense we can do it. But
ideally Oracle would be have better performance, right?
Yeah, Oracle. Yeah. So Oracle means that you sort of know that some information that you are supposed not to know. But in some case, it could be the case that, you do know, well, I want to remove reverb in this case, then you can just hint the model that you want to do reverb, the reverb. But in general, this paper is aiming for, general purpose audio effect removal. So what they want to do is try to guess what the effects are and then try to. Yeah. He says Suno. He's based.
He was at Bose, that's why I recognize the name.
Yeah. He did an internship at Bose. And he's now at Suno, based in Boston.
Yeah.
He's the go-to name in audio mixing. Yeah. AI mixing. Yeah, they have a monthly and he's leading it. And a lot of things going on in Boston, in the past, music industry, music tech companies are usually in Bay Area, but nowadays a lot of AI music startups are actually based in Boston. Yeah, and a bunch of other startups are also in Boston. So somehow they have a hub there. Someday maybe in Detroit, I guess.
You can start it.
I don't know, hopefully.
I think you might be the
unlikely. I don't think so. I mean, there should be a lot more stuff going on. Cool. Anyway, so that's two different tasks. You have effect removal and you also have sound separation, which only get you wet signals at the time. So application of sound separation, as you can probably imagine, that you can just do remixing and sampling. If you do sound separation, you can pretty much adjust the balance, or you can also do remixing if you sort of like remove the effects as well. You can also do sampling, or think practicing. Did I misspell? No. So music practicing and education. Think about, you want to practice guitars. So you want to remove the guitar from the song so that you can practice along with the song. So that's something we will see in the Moises platform. That's one of their goal. And you can think about, karaoke accompaniment generation. I say accompaniment generation, but that's tricky. But I mean, think about, I would say maybe like singing voice removal in some sense so that you can sing along. But MIR text, that's much more popular in the case why we are looking into source separation. Because oftentimes source separation is this first step for a bunch of different MIR texts. If you want to do transcription on the piano, then you get the piano track first. So you have to do source separation. If you want to do instrument and vocal detection, sometimes you do source separation to do it. Singer identification, you only want the vocal, you don't want the background. Other instruments. If you want to do lyric recognition, lyric to music alignment, then potentially you also want to do source separation so that you get the vocal track out only. And you have the instrument track, then you can sort of do lyric to music alignment. So all sort of thing can be done, or be better with source separation. Cool. So I would talk about this specific platform. It's not an advertisement, but just that they somehow give us free Moises Pro license until summer 2025. So if you're SMTD students, you likely have received a long newsletter from Excel. But basically you can register for free until summer 2025. So this is the link. Voices. Oh yeah, their company is Music Diary. I don't know how much does that cost. Yeah, a lot of startups are using .ai because well, it used to be much cheaper, but nowadays it's actually more expensive. Yeah, so it's funny. But anyway, these are the steps to get it done. So use your email, then you can get free pro license. I don't know how much that is, but likely more than $10 a month. So until summer 2025. So until the end of summer semester, as far as I know, and deadline to sign up is March 14th. So just do it.
It's 220 days.
Yeah. So how?
It's like,
I don't know.
To the end of summer.
Yeah, I think end of summer, because in the email there's a end of summer, so end of summer semester for but anyway, sign up in your desktop browser. Doesn't work in mobile app. Ignore the prompt. If they want you to put in your payment, ignore it. You shouldn't be paying anything for this case. If you like, I mean, in the future you can keep doing it, but sign up by March 14th so that you get pro license until the end of summer. Cool. We can look at this demo. Again, it's just that they give us free demos so that we are looking into this service. But somehow it's really nice anyway. So they have a bunch of different applications.
I just want to do another groove. I mean, it was a old beat that we did here. We lost the original files, so the Moises helped a lot to separate the drum kit.
This is doing source separation.
Now we're gonna put some beats. Let's try.
Let's record it.
Okay,
yeah.
Nice. We're gonna use the voice studio. We can have different vocal tones. So vox scalene.
Even though I don't know what the purpose
is. We have Barbara, Harry, Kate, and
you
Flip.
Can somehow turn your voice to someone else.
I like Philip, yeah. I like Harry.
There's actually a company that's sort of like no artist voice.
What's up? You good?
I like these chords. I think can work for us. It's a nice melody too. Perfect.
I think that's pretty much it. We can just log into it to get a sense. We would talk about, source separation mostly in this scenario. Well, one thing more, you can actually get it as VST plugin rather than going to the website. Where's the website? Somehow, well, I can click this. So I've already did that. So I've already claimed the pro license, I guess. So these are some of the songs that I uploaded yesterday. So we can get a sense. Well, how can I go back? So this is what you get once you upload the songs. You have to select what you are extracting. So in this case, I'm extracting, vocals, drums, bass, guitar, and keyboards. This is what it sounds like. The song that we just heard, right? You get the drum tracks and the bass track. Now vocals.
It's your time to party and get down like before.
Well,
It's
that's
your time to party and get down like
ignore it. The guitar are gone. They in the other track. You can imagine, mixing.
Now that's not the case, everything's in your way. Time to go back to the old days where you felt free, love of the party.
You can do all sort of stuff that you can do. Let me pause. So you can actually also do other cool things in Moesis. We are talking about source separation, but if you look at here, you can actually also post the song. Did it yesterday, so it takes some time to get the AI lyrics. You can also detect the chords so that you can play along. Actually, you can also get sort of like which is not that can do something. Oh, and there's one thing more. That's the smart. This is actually predicted by the model. So this is something called B tracking that you can, just track the beats based on your input. This will be there. Anyway, you can actually download those, export and export all. That's how I get the stuff on slides. But you could also do drums, where you can select when you upload your song. I don't know. When you upload your song, you can choose from here. You can add one single drum track, or you do 6 separate drum tracks, and that you can get different stuff. So you can also do lead vocals, background vocals. So in the case that we just saw is that you get different instrument, and there will be something anything else. There's also this multimedia tracks for film. You can do dialogue, soundtrack, and effects separation. Anyway, let's go back to the thing that I have that I uploaded yesterday. So kick drum, air drum, hi-hat, those. Just ride, I guess. And count. Oh, so you can imagine that you can potentially remix or rebalance the tracks. Anyway, feel free to play with it because we got pre-license in some sense. Cool. Questions on that? Better than you thought?
Do you know how like Lander works? That's like,
Yeah,
isn't
I
that,
don't know, but similar,
and so
right?
that's not, that's like, it's not using, is that using machine learning to actually edit the audio itself?
Yeah,
Or
Blender
machine
is
learning-
also machine learning based.
But machine learning to, instead of like messing with the audio directly, or does it mess with the compressor settings?
I
and
don't
EQ
know
settings?
in which case. You mean Blender for what? Like
Blender for,
what feature?
like AI, just like mastering.
Oh, AI mastering. I don't know how
Production.
it works actually. There's also I don't know how it works exactly, to be honest. But I never look into that, but there's also mastering here, so you can play with it. I haven't played with that. I don't know how it works. But these are the 4 things that supported by Moises for now. Source separation and the voice studio is the one that you just heard. Likely for, I don't know, content creator that they don't want to have their voice exposed. But you also have like mastering. And you can also download the plugin to use in your DAWs by, I don't know how, but click it. Then, well, you can just install it. Yep. I don't know exactly how AI mastering work. I will figure it out by the end of this course. There's just keep changing over time. If you check Moises last year, it's not like this. So things just move so fast. And nowadays, especially in the AI mixing part, is happening so fast. So things just change over time. And now native instruments, not native instrument, they combined. So native instruments and Isotope and whatever the other company is, they combine into one single big company.
Yeah.
So, they are doing a lot of AI. So Isotope is doing AI a lot in the past. And, Native Instrument now also do some AI. They have like contact, but, they also have mixing things that's using AI. So Sony owns, Sony doesn't own. So Yamaha owns Sniper. So Sniper is also doing AI. And
Oh, Yamaha owns.
Yamaha owns Sniper. That's the fun fact that no one knows. It's fully owned. So Sniper is fully owned by Yamaha. But somehow they keep the names. And it's super confusing.
Oh, the VSTSD.
Yeah, so Cubase is part of Yamaha now. Yeah, so, and Cubase is also trying to do some AI thing. And Adobe, they don't have a nice DAW, but Audition somehow, Premiere Pro somehow, but they are also doing a lot of AI things. And there's also the what platform? I think Appleton is also doing some AI. So we'll likely see something going on in the next few years, and lots of it is just being rolled out. Maybe at the end of this semester, we see something new in Appleton. There's a chance. So you can also do VST plugin to get it in your DAW. So this is like in the plugin, what it looks like for Logic Pro. Is this Logic Pro? Yeah. So pretty much the same ideas, or you can just go to the online interface to download it once you're done. There's more tutorials, but basically just play with it. It's free for us, so just work with it. You can also potentially use it in your project. Anyway, next week we will look into how it works. And that's it. And oh yeah, and so for homework 4, we will be doing source separation, but it will be much easier than the previous homework. So you've done the hardest homework. You will pass it. So hopefully you pass it. So, next homework will be source separation, but it will be, just calling some library. So pretty much you don't actually need to do any training, but, just using some existing tools. We will be using the model called Demux, which is pretty good. Not as good as the one that in Moises, but that's something you can do Python and then just grab it and do some source separation. Will release by the end of today. Cool. See ya. Monday.